Okay. By the way, I posted one video of a little bit of Galois theory sort of thing, which we did last time. So if those who want to do the Galois theory class, if it's useful, you can watch that. But yeah, I mean, it's not even completely recorded. Other 20 minutes are not there. But anyways, okay, let's continue. So maybe Aryan, if you have planned it, you can just tell us maybe whatever it is.
Yes, sir. So actually, what happened in the campus?
Ha,
So 5 days, all
okay,
anyone from Karnataka who got selected for INMO after RMO, they came.
okay. Okay,
So
so
so it was like that.
so it is state-wise, is it? Every state has its camp.
State-wise, it's like IMOTC,
Ah,
but for INMO,
okay, okay,
and it
got
is
it.
state-wise.
Ah, okay,
So and then in the camp itself, we had lecturers. Some students from IISc came and taught us. Some professors. I don't know if you know B. Suri from ISI.
yes, yes. I've spoken to him also twice in my life.
Oh,
Yes,
okay, okay. So
very
he
short
came and
conversations. Yes.
right, he came and taught us. And actually, so you know BJ Venkatachala, Challenge and
Yeah,
Present.
I know him also. I mean, I've even seen him. Yeah, old. He's quite old.
Okay, okay.
Yeah.
Yes, yes. He came and taught us,
Okay.
and some professors from IISc, some students from IISc, uh,
Okay.
and some PhD students. They came and they gave us. They would come and teach us either theory or problem solving. They'd give handouts and all that.
Okay.
Mostly Olympiad style.
Yeah,
All of
of
it was
course.
mostly, yeah.
Naturally.
So like,
Yeah.
um, and in graph theory, so we ended up in graph theory. We ended up doing up to Cayley's theorem.
Okay. I don't
Actually,
know
beyond Cayley's theorem.
what is Cayley's theorem.
Cayley's, so it's that unlabeled number of graphs. Uh, he called it equivalent, but number of unlabeled graphs, unlabeled trees on n vertices up to isomorphism.
Okay. Number of
So it,
unlabeled. Huh, okay, go on.
sorry, labeled. Unlabeled, he said it's very tough to find a closed form. Actually, there is no closed form. So
Okay.
once we label it, we can. So this will be n into n minus 2.
N into n minus 2 or n to the power
Sorry,
n
n to
minus
the power. N to the power. Yeah, my
2.
bad. Yeah.
Okay. Okay.
So we equivalently formulated this. I actually forgot what the term used was, but some rooted trees. For that, we showed the number will be n into n to the power n minus 1, and then from there, that
Huh.
result is equivalent to this actually. So from there,
Okay.
we derived this.
Okay. Okay. But so since you've talked, okay, you call this Cayley's theorem, right? I
Yeah,
mean,
yeah,
I
Cayley's
should
theorem.
say it is Cayley's theorem. Okay. Yeah. Yeah.
And then we actually also proved Euler's, one part of Euler's theorem, that even degree graph, if and only if there exists an Eulerian path.
Uh-huh. Eulerian circuit
And
or Eulerian path. Okay.
yeah, path. He called it path. And
Path. Okay.
we also discussed the algorithm, that if you have an even degree graph,
Uh,
what is the algorithm to find an Eulerian cycle path, or yeah, like that.
okay. Maybe I'll write
Floiry's algorithm.
algorithm for
Yes.
Eulerian path. What is the name you said?
Floiry. FLEU.
FLEURY.
EURY. Yeah, Floiry's algorithm.
Okay. So I think this will occupy us. This is, I think, yeah. So we should maybe
No,
go into
not theorem,
details.
sir. Algorithm.
Oh, yeah. I am just always, yeah, right. Used to writing theorems, but
Yes.
algorithm. Okay. Yeah. So let us try to understand what this means because I have been a long time. I have not studied.
Okay.
Yeah.
So
Maybe you can give us some
so
small example of this. Explain it to us. This.
correct. So we did it for I think it's best to do it for n equal to 4. We can try it for
Okay,
n equal to
n
4.
equal to 4.
So
So
do I have
Vaishnavi,
to? So
yeah, so we are not defining these things concretely first, but as Aryan, as you were saying, like you can give us the example, and through that you can explain us. Maybe.
okay, okay. So
Anyway,
basically, yeah, graph. I know. I think everyone knows. And tree is so basically a tree is a connected graph. Between any two vertices, there exists a path.
right, and there is no cycle.
Informally. Yeah, and the special thing about tree is there's no cycle.
There's no cycle. Okay, these two
Yeah.
things. Okay,
So now we're looking at the number of labeling. So if we draw four vertices, collinear,
okay,
just say
uh-huh.
collinear, sorry, yeah.
Okay,
And sir, can you join them up here?
yes,
Now if we label it from top to bottom, 1, 2, 3, 4, that would be the same as labeling it top to bottom 4, 3, 2, 1. So we say that these two graphs, these two trees are isomorphic. So we do not want to count these as different, actually.
right. Okay.
Yeah.
So the first thing is that this is an example of a tree, right?
Yes.
Okay.
A tree.
and
Yes.
and these two things are, we say that these two things are isomorphic.
Isomorphic. Yes.
Okay, so through this, Aryan, can you give any example of okay, sorry, can you give a definition of isomorphic graphs or something like that?
Definition, even like he didn't define it properly. He just said, I think you guys know what I'm talking about, and he went about it. But
Haha.
from,
Okay.
I think what you can say is, I wouldn't say, mm, I don't know how to put it, sir, but
I mean, it's just a matter of, I think, translating. So I'll just say it. I mean, it's
translating or
we can
something
all
like that.
just
Yeah.
like sort of do it. If we sit down for 5 minutes, we can come up with the definition.
Yeah. Yeah. Yeah.
But
Yeah.
I'm just going to say it, okay, so that it's yeah,
Okay. Okay.
fair. So we basically, a graph is, as you know, is a set of is a pair, okay, set of vertices and then a set of edges. Okay, for example, in so let's say if this is my graph T, okay, the in T, this V is equal to uh, V is equal to 1, 2, 3, 4. And also here the condition is that E is a subset of V cross V. Okay, and that's what a pair edges mean, right? So it's a subset of V cross V, or I mean, there are equivalent ways to say it, but maybe I should say unordered pairs, because we are dealing with undirected graphs. Okay, is a subset of, like, this is a little, this part is not so useful in the beginning, but it could be useful when you do theoretical arguments, or if there is a confusion, are these two isomorphic, then you go back to the definition and you resolve it. So anyways, I mean, yeah, so unordered pairs of vertices. Okay, it's a subset of that. I mean, that's what H should be, right? So that's just an H. And in our example, E is equal to. So Vaishnavi, can you just tell us what do you think should be the set E in our example?
Oh, it's 1, 2, like the edge 1, 2,
Right.
2, 3,
Yes.
and 3, 4.
Perfect. Yeah. So I was just checking, like, if the definition is clear. That's all. Okay. So it's correct. So otherwise it's easy. So nice. Okay. So this is just what happens in our example. But now, what is an isomorphism? This is, I just give the definition of a graph. So, well, an isomorphism would be, we say that this graph is isomorphic. Has anyone formed the definition? I mean, if there exists bijection,
Yeah, it's vertices and edges.
so what happens to the edges? Because the bijection is on the vertices, or
Okay.
you want to say bijection is also on the edges, right? But
Yeah.
exactly that is exactly what we have to say. So we have to say that such that uh,
So I think
hmm,
any two vertices, like in the first graph, if they're adjacent if and only if they're adjacent in their images
yes,
are adjacent.
yes, exactly. It's the most obvious thing. So I'm not saying anything new, but just saying it because yeah. So VIVJ is in E1 if and only if, or it is enough to just actually say, no, it's not enough to say one direction. I have to say if and only if phi VI, phi VJ is in E2. This is the same thing. This can also be said more abstractly, like phi. You could just say that phi of E1 is equal to E2. If you allow phi to be defined on the pairs. Same thing. So this is the notion of isomorphism. So what is the bijection in our case? What is phi?
It is the way I defined it.
Hmm.
I don't know if I'm using the right notation, but it's a cycle. Like it sends two to
Right, it's a
three, three to
cycle.
one. Yes. Yeah.
Right, yeah. You could say that it's a cycle. Yeah, one goes
Yeah.
to no, but yeah, it's a cycle. Yeah, it is reverse.
Yeah. Yes. Yes.
No, no,
Like the
two. Okay, but one
two
goes to
goes
four.
to. Oh, correct. Correct. It's not a cycle actually. Yeah. Yeah.
Yeah,
It's a
it
reverse.
is.
Yeah. Yeah.
It's a cycle, but in the reverse order. Yeah. So two
Yeah. Yeah.
goes to. Oh no, no. So what is it?
Two goes to three. One
Yeah.
goes to four.
So
Yes.
you're right. It's not a cycle actually. It's not a cycle at
Yeah.
all. Yeah. Yes. Uh, so this is like one isomorphism. Yeah. Or is it an isomorphism? Yes.
Yes. Yes.
Yes. Uh, yeah. Yes. And what if we send 1 to 1, 2 to 2? Will that work? Would that have also worked?
Yes. What? Yeah. I mean, every graph is isomorphic to itself.
Yes. Right. So then where are we? So but that sounds like something not. What you said is correct, of course. But what I am trying to say is that then is something wrong we are doing?
No. So this is correct only. Like, are you saying will it come up when we're counting the identity like that?
Uh, no, not
Mm.
like that. What I'm saying is that, like in this, of course, if we would have sent, if it was something stupid, I'm saying that if we just define the isomorphism to be the identity one,
Okay.
if we
Yes.
just define if we take phi to be the identity, that would
Okay.
also give an isomorphism between T1 and T2.
Yes. But no, in that case, T2 would be equal to T1, like fully equal, not just isomorphic.
Yes. So yes, exactly. That's what I'm
Yeah.
saying. So in that case, this is a very special kind of isomorphism. Uh,
Yeah. I didn't
right?
understand. Special, like,
Especially in the sense that the identity map also is an isomorphism.
yes. Yes. Yes.
Right. That doesn't happen for all isomorphisms. Right. So let's
Of
let
course.
yeah. So let's try to come up with an example like that. Right. So let me first write a little bit here. So uh, I will just what we want to say is that phi equals to identity works for this example. But now, can we cook up an example of a
So,
graph where identity doesn't work?
but it will always work, right? Because
Did it
Vi,
all?
comma Vj is in E if and only if Vi, comma Vj is in E.
No, but no, what
Bec-
I'm saying is you have to change the graph, of course. You have to change these two graphs. So for for
oh,
this pair of graphs, the identity uh, map works as an isomorphism. We want an example
no,
of
uh, so for this pair, so if we take this to be T1 and T2,
uh,
then directly the identity won't work because phi will send T1 back to T1. So we can't show that T1 is isomorphic to T2 like that. So like
but okay, but I'm saying that if I send 1 to 1, 2 to
okay,
2, 3 to 3,
right.
this gives
Yes.
an isomorphism, right?
Between T1 and T1, not T1
Between
and
T1
T2.
and T2. Why not between T1 and T2? That's my question.
That's
By definition, it
okay,
does,
okay.
right?
But
I mean, I understand you meant to say this one and this one are
okay,
different.
okay, okay, okay. Oh, I see, I see, I see. Yeah,
So,
yeah, I
yeah,
see what you're saying.
right. But I mean, if you just now,
Mm.
if I change, if I make this, maybe if I make this 2 and
Two,
3, then the
three.
identity does
Yeah,
not work.
yeah.
But still, they
And
are
in fact, I don't. No, I don't think they're isomorphic. So because
no, they are
actually,
isomorphic.
yeah, but not when we label them. Because
Uh,
two, the vertex two,
uh,
originally is connected to 1 and 3. Here it is, I think, something else.
but no, yeah, but if I
They are
take
not the
1 to,
same.
yeah, they're right, they're not the same. But if I consider this map, then is it not an isomorphism?
Sending 1 to 4, 3. Yes,
It is an
it
isomorph.
is. Oh,
So,
no, no, sir. But actually, the edge 1, comma 2,
hmm,
here it will form the edge. Okay, that
4
is
comma
correct.
2, and they are isomorphic.
Okay. Yes, yes, yes.
Yeah,
But
right?
it is the okay. Yes, yes. Yeah, yeah. This is isomorphic.
Maybe you want to call them different in your problem. That I do not know. But by definition of isomorphism, they are isomorphic.
Yeah, yeah. Yes, yes.
Okay, yeah. I hope this is clear. Okay, Vaishnavi, I hope this is clear. If something is not clear, tell us. Okay.
Yes, yes,
Yes,
yes.
this is okay, easy. So yeah, right. But so Aryan, do you want to call these two isomorphic? Uh, is it fine to call these
Yeah,
isomorphic?
they are isomorphic. Yes.
So in
Yeah, yeah.
Cayley would count them as same, right?
No, no. I just saw the some list. Yeah, this won't be counted as the same.
Oh, then what's the definition of isomorph labeled?
Oh, I mean, sorry, they will be counted
They
as the
will be
same.
counted.
Sorry,
Okay,
sorry. Yeah,
that's
they will
good to
be
know.
counted.
Good to know that,
Yeah.
right? Okay, otherwise it would be, uh, yeah,
Yeah.
yeah. Otherwise it would be something very different. Okay, now you should continue. So sorry for the very
Okay,
long.
okay.
Yeah. Okay.
So for I think it's best if we start with a smaller case for n equal to 3, maybe.
Okay. Yeah. So let's do that.
Oh, and one more result. I think easy to prove. So I'll give a list of important results on trees.
Huh.
So
Okay.
a tree on n vertices has n minus 1 edges.
Right. That is okay. So n
Yeah.
vertices imply n minus one edges.
Yes. Uh,
Right.
and removing any edge from a tree,
Hmm.
uh, they call it deforestation. The term is literally deforestation. It deforests the tree.
Yes. So you can see this is the tree, and if you take out this edge, then it becomes disconnected. Right? You
Correct.
take
Disconnect.
any, yeah, or deforest.
Yeah.
So these are facts, and Vaishnavi, if you have never proved them, then you should try to prove them. Okay, that if you take
Yeah.
any tree, then it will have. These are good exercises in discrete, reasoning with discrete objects. Okay, and
Yeah.
if you
Yeah.
take out an edge, and it becomes disconnected. Okay, good.
And one more thing. Given any tree, if we add an edge that was not previously there, we
Mhm.
will create a cycle.
Right. It's also there. Yeah. And this is precisely like what happens in linear algebra, right? You have so how do you say
Yeah,
like it's
like even
like
I was reminded,
yeah,
like
right.
everything in the tree, like every edge is very important. You can't remove or you can't add. So like I
Yeah.
forgot what it reminded me of, but it reminded me of something in linear algebra, right?
Right. Yeah. So it can be completely formalized in terms of linear algebra, and both can be axiomatized into metroid theory, which are very active areas of research. Yeah. So, anyways, yeah. So let's continue.
And every tree has
Mhm.
at least two leaves, where a leaf is a vertex with degree 1.
Okay. Fine. Mhm. Let's. Yeah.
I think that there's an easy proof. So
Okay.
consider all the paths between all the vertices. By definition, because tree, it will be there.
So you're proving every leaf has at least two leaves. Every tree has
No,
at least two leaves.
yes, at least two
Okay.
leaves, yes.
Okay.
Consider all the paths that you get.
Uh,
And since it's a finite list, there is some maximum. So pick up the maximum path,
uh-huh.
longest path. Yeah.
Okay.
The endpoints of okay. Oh, that was actually wrong then. Hmm.
At least two leaves.
Uh, at least two leaves from here. One endpoint uh, will necessarily be of degree 1.
Right. Yeah. Yes. So that will give you one
Now,
leaf.
yeah, that gives us one leaf. Now that we have one leaf, I'm just giving the sketch of the proof. From induction, we can show that there must be another leaf in the tree.
Yeah. You can do something. I mean, yeah.
So
It's
yeah,
yeah. It can
that's
be
an okay
done.
proof. It's easy only.
Yes. Yes. Yeah. Yeah, let's get to proving this thing. Yeah. Cayley's theorem. We want to get this n to the power
Correct.
n minus two.
Yeah. So for n equal to 3, we will do.
Hmm.
So for n equal to 3, we know that there are only two edges.
Sorry, I should write. Yeah. Okay. Two. Yeah. Right. We are only two edges. We know that.
Yeah. Yes. So I think if we make it like a triangle, it will be easier. Or it doesn't matter, but yeah.
Oh, sorry. N equal to three. I was getting it wrong. So
Yeah.
we should make it like a triangle.
Yeah.
Okay.
So so can you draw the edges between?
Yes.
Yeah, and some two. Yeah. Now now if we notice, we can name it say 1, 2, 3. Yeah. Or we can name it 3, 1, 2. And actually, so these are counted as different. So yeah, I think some isomorphism.
Yeah. So it should be just not up to isomorphism, I think.
Equivalent. He said equivalent. I
Yes.
think maybe that means something else.
Yeah. So we have to get the. I mean, it's good. I mean, that's how we learn, right? Like
Yeah.
when you try to solve it, you see, oh, then it's
No,
wrong.
but
If
actually, he did use the term isomorphism. Even in the thing, like his statement of the theorem, he wrote up to isomorphism. But he
yeah.
used the terms up to isomorphism and equivalently
No.
interchangeably. So
But you see,
I don't know
as we
what.
are as we are also seeing, as we can see, counting up to isomorphism would be difficult. Okay.
Yeah, that's always difficult. So.
Yes, like counting the number of partitions is difficult, but of a number,
Yeah,
as you know, all that. Yeah. So yeah, it should be up to not up to isomorphism. Let's tentatively strike it off, and let's see.
eh, let's just say equivalent, where
Hmm.
intuitively you can get one graph from the other by just moving it around, just
Yes. Yes.
doing something like that, not
Ro-
changing the order between the
Yes,
edges like
yeah.
that.
Yeah. So these are I mean the correct term should be labeled unordered trees.
Yeah.
Unordered. I mean that's what because on a yeah. So we will
Yes, yes.
yes we will see it. I think so. This thing. So tell me if so you would want to consider these as the same. Do you want to consider these as same? I mean, these two?
Yes,
Ah, so that's the thing. So
yes,
unordered
that
on
is the
one.
yes.
Yeah, yeah. Now
So
we are
these
not
two would be considered.
right, correct. So
Correct,
let's
correct.
go on without defining unordered at the moment. But
Right now, there should be only one tree left, and that is right. There is only one tree left. Yeah, three. So it should
yes.
be two below.
Ah, yeah, of course.
Yeah. So now the formula should give 3 to the power 3 minus 1. So yeah, 3 minus 2, sorry. Yeah. So these are the three trees. So this is what we want to count.
Right. Yes. So
And
yes.
for n equal to 4, there are 16, but there's actually a very good way to first classify them and count them. So for n equal to 4, they can either form a line or a bigger triangle like this. Like they can form a cycle. They can all be in a line. What I mean by that is every degree is of vertex 1. We can have that.
Okay. That's what you mean by they are in a line.
They are in a line, yes.
But every vertex cannot have degree 1. Maybe you want to say at most 2 or
Um,
something.
no, it can have.
Degree 1. Okay.
Oh, okay. No. I'm sorry. Yeah.
Then every vertex
It's in a
will
line.
be.
Yeah, that's all. It's in a line. That's
It's in
all.
a line. That's what you mean. Yeah.
Yeah.
Path. It's
Path.
a
Yeah.
path. And you can, of course, characterize path in many complicated ways, but you can just say it's a path.
Yeah. And from here, we can count permutations. We'll get 4 factorial. But we have to remember to divide out by 2. Because rotations of this will give you'll be counting the same thing. Like what we did last time. So 4, 3, 2, 1 is the same as 1, 2, 3, 4. Like that, I mean.
Why? It means that why does that fit in the order of why does that fit in the definition of unordered? So why do you want to say these are same?
We say that these are equivalent because we can rotate the second one and get this one.
First.
Yeah.
Okay.
So, and one more thing,
Hmm.
this labeling. So if we see this labeling in the first graph, 1 is connected to 2, 2 is connected to 3, 3 is connected to 4. Second graph also same structure is there. So we can say
Right.
that the edges are
Right.
like
Yeah. So basically it then sort of means that you are considering these as rigid objects, right?
yes.
Where the only motion you can make is at these things, right? Like you can only move it at the vertices, but not break,
Correct.
Right? It's like a mechanical system where you
Yeah.
can only, yeah, I get it. So you can
But an
rotate.
isomorphism is something more general.
Yes, of course, it's much more general. It doesn't regard the structure. Yeah, it's different. Yeah. So this is like in
Yeah.
chemistry, the compounds, the
Okay.
isomers, and I suppose, right?
Oh,
Where you
correct. Exactly.
stereo, yeah, you can. Okay, so then I think now we
So,
have a more clear definition of unordered. So that later, if
right.
you people, or maybe if Vaishnavi, if you're trying to understand what group action you can do on the collection of graphs, so that the orbits are precisely the isomorphism classes under this definition of unordered, so that every orbit is precisely the collection of all the unordered things. Yeah, you understand. Then if you want to guess which group you should act by or something like that, then this definition would be useful, right? And you should keep
Yes.
them. Okay. Then there is
Now,
case 2.
case 2 where there's one vertex of degree 3 and the rest are of degree 1.
Okay. One vertex of degree 3. Okay, let's just do
Yeah.
this case. If there is one more case, maybe we'll not do that.
No, this is the last case.
Okay, this is the last case. That makes sense, right? Because there can only be one vertex of degree 3. Yeah.
Yeah.
Okay, and in that we can again count it out. But tell us how.
Yes. So
Just choose. You have, it's like 4 choose one or something.
now we can just count, and now here we'll be dividing by 3.
Okay, what will you divide by 3?
So whatever you count, once we count, so I think it's better if you write the last vertex above, so it looks almost like a triangle.
Like this? Or no? No.
No, the last vertex, yeah, write that one above. Yeah, above
This?
that. Yeah.
Okay.
No. Like, you make it look like a triangle, sir. It'll be easier to see in that case.
Make it look like a triangle. You mean like this? It look like a tetrad.
No.
Oh, sorry. Yeah.
Yeah,
You want to
yeah,
look.
almost like a, yes.
Okay. Okay, like this?
No, make it look like a star. So,
Oh, like,
uh,
okay. I'm sorry. So this should be the center.
yeah, yeah, like that.
Okay,
So now it's
got
sort
it.
of easier to see. Yeah.
Okay.
Okay, now we have to count. So naively, our first count will be 4 factorial,
But okay, yeah.
and then we will be dividing by
But why is it not
2
just
into 3.
4? Exactly. So it's just 4 because you choose what vertex you place here. And the others
Yeah,
you can just rotate
others you can, yeah.
as we
The way
just.
I saw it was, yeah, but the way I saw it was 4 factorial is our first count. Then we
Mhm.
divide by 2 for reflection across the center line, and then we divide by 3 for the 3 rotations. So like that.
Okay. Cool. Yeah, that's perfect.
Yeah.
Yeah.
So that.
Yeah.
So
That's fine.
now our answer will be 12 plus 4, 16 as expected.
Ah, nice.
Right.
Great. Now you tell us the final way.
Okay. So the
How do you
final
get?
way,
Are you going to use
so
some? Yeah.
rooted, I think have to introduce the term rooted trees.
Oh, but did you also not do the proofer code method?
Sorry?
You build a code, proofer code.
Code.
Yeah. No, code meaning it's an encoding. Did you not do this?
Oh, no. So what is this? Maybe maybe he just didn't
Yeah,
bring
he
up the
just didn't
same.
say it, maybe. Yeah. So, I mean, n to the power n minus, because this is the way I know. There is also a method by linear algebra, determinants and stuff. But n to the power n
Oh,
minus 2 is what? It's basically the number of ways. So basically, you have n letters and you have n minus 2
and you're
places.
making n minus 2 binary code. I mean, n minus 2, something like that. Yeah.
Yes, yeah. And you want to fill this. That answer is this,
Making
right?
the words. Yeah,
Yeah,
that's also this.
exactly. Making
He
the
did
words.
mention this. He
Yeah.
mentioned something about some matrix, some special matrix that you can assign to every tree or every graph in fact,
Maybe
and you
adjacency
can say
matrix
something.
or something like that.
No, he used some very
Laplacian.
so the name of the matrix, it had a mathematician's name actually, so it's not
Laplacian.
some
Laplacian.
uh no, Kirchhoff's matrix tree,
Yeah,
something he said.
Yeah. So that is called the Kirchhoff's matrix theorem, and that comes from the Kirchhoff's law in physics,
Oh,
in the
oh,
electricity.
that.
Yes,
Oh,
yeah, yeah,
okay.
it's that law, and that is actually has good consequences in spectral graph theory. If you read,
Oh, I see.
because place it and then it like the current has to add up, and that kind of law actually
Oh,
gives you a lot
right.
of results in graph theory easily. Like, yeah.
Oh, okay, that is very interesting.
Yes,
Yeah.
you should read about this, and you should also read about this. So what this does is basically it takes the tree, looks at the labels, and using that it makes a code. For every tree, you get a word, and you get a bijection between the word, but you have to give a way to get the word from the tree and back.
Yeah, some yeah. He said we can do that,
Yes.
but he said he wanted to introduce the concept of rooted trees.
Yes. So
And
maybe so you can tell us the rooted tree method. You have 3 minutes. So let's see if you can.
okay.
Yeah.
In three, so first he takes a rooted tree. A rooted tree is a tree in which there is some vertex that has been designated as a root. That's all.
Okay.
So what we can do, given any tree, we can pick some vertex as the root, and any vertex.
Hmm. Okay.
And then once we pick it, these edges, they can be assigned some we can write them in some neat way or some natural way.
Okay.
So we can equivalently write this graph once we pick the root in some nice way. So for example, we can put the root at the top, and then like what you've written now is some of the structures that he was considering. So like that. And then what we do with 1 second, sir. So once we have these rooted trees, he introduced a few. Okay.
Yeah,
1
no
second,
problem.
sir.
So the goal was to count rooted trees
Yeah.
because
So
it's
once you
easier,
count,
and then you divide out.
correct. So once you count, so what you can do once you've introduced this rooted trees is you can equivalently formulate Cayley's theorem in terms of these rooted trees. And that will give you a sort of double counting proof. Yeah. So then, okay, yeah, got it. So now we will compute the number of different sequences of directed edges. So now from edges, we're moving to directed edges.
Okay.
So to each edge, we give a direction. Like
Any direction.
the way. Consider the path from the root to the, not any direction, like that.
Okay.
And as, root is at the top. So something like that. This is not exactly precise, but we are counting the directed edges. So now we are counting the number of different sequences of directed edges that can be added to an empty graph on n vertices to yield a rooted tree.
Okay, now you want to build the graph from scratch.
Correct.
Yeah, and that's the proof of code idea is also same. So I think these are the same things.
I see.
Similar things, yeah. But anyways, maybe the time is up, so maybe we can just meet on Google Meet and then we can decide.
Okay.
Yeah, no problem.
Yes.
I mean, that's how it is.